go. Okay, so just to establish a few things about limits, and actually this particular question, I mean, I chose a different graph and some different limits, but there's ones like this in the homework and in the review, and I really walked right up and chose one of these and asked very similar questions. And what this question is asking really is, do I know what a limit is? Do I know what's going on? And if you don't know what a limit is, here it comes. A limit is where is the function heading towards? It doesn't have to be there. It's just where is it heading towards? So the first one, a very strange graph. I will not pretend that this graph comes up in some application or something like that. Just a graph set up to test your knowledge about limits. So here we go. Limit as x approaches 0 of f at x. Okay, it's easy to get this question wrong because you go, oh look, I get it. I know what a limit is. As I approach x value 0, what's the y value headed to? And it's awfully tempting to say 1 here. Why is the answer not 1? Damn it. Because you can't come at it from the left. That was something we sort of touched on in advanced functions, coming at something from both sides, but we didn't hammer it down. Now I'm hammering it down. You've got to be able to come from both sides for the limit to exist. If there's a little plus or a minus, then you're allowed to come left or right. But this one asks for the limit. So this does not exist, and you can use the short form DNE if you want. Instantly, if you're so worried about having this and you're worried about copying it down, hey, it's going to be on the video. It's going to be on the completed version, so you'll be able to look back at it, no problem. Limit as x approaches 1 of f at x. Okay, now I can come from both sides. I come in from this side. As I come in from this side, the function's heading towards 0. As I come in from this side, it's heading towards 1. This one asks for limit as x approaches 1. Is the answer 0 or is it 1? He said, setting them up. It doesn't exist because the answers don't match up. When it is written like this with no plus or minus there, it's saying, do the answers match up? That's what it's really asking. Do the answers match up? And they don't match up. They don't head to the same thing. And if you're out there going, well, why do I care if they match up or not? Hey, we're only days away from this all tying together and going, oh, that's why they had to be the same from both sides. Okay. Another does not exist. Limit as x approaches 2, a very tricky one. Very tricky. As you come in from this side, this function's heading towards a y value of 1. As you come in from this side, it's heading towards y value of 1. But it's not there. It doesn't exist there. It's a hole, and it's another dot up here. What is the answer? And then I'm dying, if somebody gets the right answer, I'm dying to know what's going through their brain to get the answer. Brad, what's the answer? The answer is 1, and that freaks people out. But what is it about limits that allows us to completely ignore this other little dot that's sticking up here? No. Just what it's headed towards. The limit is what it's heading towards. All these pieces are going to come together probably tomorrow in a lesson called continuity. And continuity means it's got to head towards something and it's got to be there. To be continuous, those things all got to match up. You got to be heading towards something and it's got to be there. So yeah, there's a big picture going on here. For now, the limit part of it is just what is it heading towards? Is it heading towards the same thing on both sides? And the answer is yes, it's heading to 1 on both sides. How about as x approaches 3? That's the easy one. No little tricks, no overthinking here. What's it headed towards? It's heading towards 2, and it actually is 2 there, making it continuous, which gives away one of the later lessons. That's all the continuous lesson is. What it's heading towards also has to be what it is for it to be continuous. Any questions on those? If you're like, I totally get that, then you're 4 marks into the test already going, yeah, I got it. Now, just think about this for a second. I already told you that there was those 4 methods on there. Those are all 3 marks each, 12, 16. We're already 16 marks into this test, knowing exactly what's coming. Yeah? Okay. Oh, one more. Limit as x approaches 4. It's heading towards 1. No, it's not. It is. Well, it is heading towards 1. If this said limit as x approaches 4 from negative, then I could say from negative, it's heading towards 1. But it's not heading towards anything over here. It's worse. There's nothing even out there. How can it head towards something when there's nothing out there? So this doesn't exist here. Questions here? The formal definition of a limit. Oh, this is ugly. Now, let me just tell you the whole history of this little statement. This statement is the formal definition. It's rigorous. In math, we use this word called rigorous, which means, hey, this is good. This is proved. Like if you go back to grade 9, the Pythagorean theorem, when it was first presented to you, wasn't rigorous. Just somebody went up and said, hey, this is the way it works out. C squared equals a squared plus b squared. Meanwhile, the quadratic formula was rigorous. In class or in your textbook, they prove it. They go, this is exactly what the quadratic formula is. The limits so far, I've been sort of like, oh, it's like this. This is how it works. Not rigorous. This is the rigorous part of limits. Now, we have a problem. To really, really understand this, we have to get sidetracked for a day or two, for a class or two, into the formal definition of a limit. And it's great stuff for AP Calc. We definitely want to do it. The question is when to do it. We don't have time right now. I've got to keep us on track on the important things for now. We will get distracted at some point. I'm guessing it'll be about March, because I want you to really see this before you actually do the AP exam and before you head off to calculus and university. But it takes time. And it's a really tough exploration. So we're going to give it some time. I'll give you a little taste of what this is saying. Don't worry about the symbology. Let me just give you a taste of the idea. And to do that, I need to go back to that advanced function lesson I had up yesterday. If I can find it quickly. Rates of change. Instantaneous rate of change complete. I'm hoping this is exactly what came up. Oh, yes, it is. And we'll go fit to width. No, we'll go best fit. There we go. Okay. Let's just talk about this situation again. Back when we were first learning about limits, but we didn't know we were talking about limits. By the time we were done this table, we decided that the answer was 15.2. Okay? We went down all the way through here. We said, okay, it's 10.3. No, it's 12.75. We got closer and closer, and it started to settle into an answer here. And what a formal limit is if this answer is 15.2, if it truly is 15.2, then what we should be able to do is get as close to 15.2 as anybody wants. So your boss comes up and says, hey, I'm fine with 15.2, but I have to make sure it's within tenths. You know, it has to be that close. And I go, oh, it already is. I only have to go this far. He goes back to do his work, comes back and says, I really need it within thousandths. And it's not really within thousandths yet because it's got 195. I need it to be 15.199. I go, no problem. I can get it to 15.199. I'll just keep going. Yeah? Comes back the next day. No, I need millionths. I can't believe it. I need 199999999. I need it that close to 15.2. And I'm like, it's no problem. I'll just keep going. And if 15.2 is truly the limit, oh, big sentence there. If 15.2 is truly the limit, I'll be able to get as close as anybody wants to. You want 1999999 all the way to Pluto? No problem. Just give me a year or so, and I'll get you there. Okay? If it's the limit. If it's not the limit, eventually it won't match up. You know, eventually I won't get there. Maybe the limit's actually 15.19995. You see, at some point, I won't be able to get any closer to 15.2. It'll break away. It'll start going towards this other number. So, if it's truly the limit, I'll get as close as you want. Yeah? Well, that's pretty much the explanation of what's said here. And this is your first version of this. This is not on your test. We'll do an assignment on it way later. In the second quad of this course, where we've got some time. We'll have some time to say, okay, let's really explore this thing. Okay? But let me read it once, so your intro to this. Assume f is defined in a neighborhood of c, and let c and l be real numbers. That's just setting it up. We're talking about some function f, and we've got two numbers c and l. The function f has a limit as x approaches c if you give any number you want. You want to get within epsilon of it. You want to get to tenths, hundredths, thousands, whatever you say. I'm waiting for it. I'm like, go ahead. Give me any epsilon you want. Any distance you want to get within the limit, I'll eventually tell you, you just have to get this close delta-wise with the x. You want to get within 0.01? Maybe I've got to get down to 0.001s on my x's, something like that. If that sort of makes sense, you go, oh, that makes sense. If it is the limit, I'll always be able to get as close as you want. That's a good first intro to this crazy statement. The proofs of this and using this are insane. Probably a full 80-minute lesson for me to teach how to use it, and then some crazy practice. But it's really a bicycle concept. There'll be a point where it just clicks and you go, oh, I totally get it now. And we're going to do that. And it's thrown in here for now, but we're not doing it right now. Basically speaking, if a point is the limit, if someone says, please get within epsilon of the limit, I just say, okay, that means I've got to get within delta x values to be able to get there. Okay? And this is, how would you like to go further? And last year, when we had tons of time, they voted yes, and we did the formal stuff right then within the chapter, and we just moved everything back because it was regular semesters. We had time to do it. We don't have time right now. We'll get back to this later. This slide you can actually put beside it. Ooh, don't worry about it. You can actually write in the slide. Don't worry too much about this right now. It's just a little intro to that. There is formal definitions of the limits out there, and that slide could remind you of the grade 10 quadratic formula lesson where the teacher proved the quadratic formula. It's all very nice, but you don't really need it just yet. Okay. Question for discussion. Can a limit be distributed over addition? Some great slides coming up. These slides basically say limits behave well. We can use the rules we would expect to use. This didn't happen with sine and cosine. When we got to distribution on sine and cosine, things went haywire. And the trig toolbox is what developed. Said, can we do distribution? Can we just add, subtract, multiply, divide these things any way we want? And the answer is no. You're going to need the trig toolbox. What a mess. Log laws didn't follow the rules the way we wanted. And you had to come up with log laws. Limits, we're not going to need any crazy toolbox. Limits do what you would expect them to do. You can distribute limits like this. If you want to find the limit as x approaches 2 of x squared plus 2x, you can just sub the 2 into the x squared and sub the 2 into the 2x and add them afterwards. And what I mean by distribution is you can change the order of what you're doing here. This says find the limit of two things added together. What you're totally allowed to do is find the limit of each one and add them together afterwards. As you would hope that limits follow nice rules like that, and they do. Will it always distribute over addition? Yes. Limits behave so nicely. It's not clear exactly why. I haven't proved that it's true, but it is nice for doing questions. In fact, you probably already used this last night in the homework when you subbed into a polynomial. You just subbed into the individual pieces. You didn't think about it. You go, oh, I'm totally allowed to just sub in as I go. Let's consider a graphical explanation as to why you're allowed to sub in for limits. Consider this function. Oh, old friend. It's some kind of parabola type deal. Looks like it's been horizontally compressed or vertically compressed or horizontally stretched. And let's just talk about the limit as x approaches 5. This is not a particularly tough question. As you approach 5, this function approaches 5. I want my pointer. Oh, it does it. Anyways, okay, don't worry about that. As you approach 5, the y value approaches 5. Not complicated. The limit as x approaches 5 is 5. Here's another function, g at x. And what's its limit as x approaches 5? Okay, so this limit was 5. On the line, though, here comes some more lines. Here we go. It was equal to 1. Nothing too complicated so far. I've got two functions. I'm finding both their limits as x approaches 5. Now I'm going to graph on there f at x plus g at x, the function where these two functions are added together. There it is there. What do you think if we just take the two functions and add them together to get this? What do you think is going to happen to the limits? They're just added together. Of course they are. Yeah, it's like graphically almost obvious that that has to be the way. The functions are added together, so the limits would be added together. And that's all this part of the lesson is saying, something pretty easy, that if you want to find the limit of two things added together, find each limit if you want, and then add the answers together afterwards. That totally works. Oh, and it gets better. It gets way better. You can do it with adding. You can do it with subtracting. You can do it when there's a constant being multiplied. You can do it when they're multiplied. You can do it when they're divided. Hold on. You can do it when they're divided as long as the bottom doesn't come out to be 0. That's always been a thing. When the denominator is 0, we start to freak out, right? So we'll get to more of those later. If you want to find the limit of just a constant value, it is the constant value. We ran into that yesterday. Limit as x approaches 3 of the number 7, it's just 7, right? Oh, and even exponents. You want to do the exponent first? Great. You want to do the exponent after? No problem. So limits, it's like giving you free reign to just sub your brains out. Go ahead, sub to get limits, unless something goes wrong. What's the thing we ran into that can go wrong that's going to make us do some other type of work? What fraction can we get that's going to be like trigger other things? 0 over 0. So sub. Then you get 0 over 0, and then you've got your 4 choices based on, and those choices, the choice should be easy. Should be like, oh, it's an absolute value. I know what to do. Oh, it's a square root. I know what to do. Right? Here's an example. As tough as an example as I could come up with of how to use this thing. Please complete this following on a separate page. Oh, okay, I've got to go on to a separate page here. You find a separate page. I'll get a separate page here going. Do I know what I'm doing? Yeah. There. Woo. Are we ready? This is as tough as it gets using what I've just showed you. And I hope by the end you'll be like, oh, okay, that's really no problem. This says find the limit as x approaches 3 of this whole big mess. Now, whole bunch of steps that you can sort of skip. Once you see all the steps at once, you'll be like, oh, I can skip over a lot of that stuff. The only thing I know is that the limit as x approaches 3 of f at x is 5. That doesn't seem to help me at first until I start using the limit laws I just saw. One of the limit laws says if you've got 2 things that are being divided, you can find the limit of the top, the limit of the bottom, and then divide them afterwards. You don't have to do divide first. So I'm going to do limit as x approaches 3 of the numerator over limit as x approaches 3 of the denominator. All I've done is distribute the limit and say, no, I'm going to do limits first, and I'll divide later. I'm going to go one step farther. Limits can be distributed over addition. Instead of adding these 2 things in the numerator and then finding their limit afterwards, I'm going to find their limits first, and I'll add them later. So I'm going to find the limit as x approaches 3 of f at x plus the limit as x approaches 3 of x squared. And I'm going to do the same thing on the bottom. And again, by the time you watch me do this whole thing, you might be like, I can totally write this faster. There's no reason for all these steps. The reason I'm doing all the steps is so that you see exactly what I'm up to every step of the way. I'm going to go up here just so we don't lose visibility for you there. The numerator's ready. I can do the numerator right now. The denominator's not quite ready because it's still got this square to deal on it. So I'm just going to rewrite the numerator. And okay, this says square f at x, then find its limit. Well, I'm just going to do it the opposite way. The limit laws told me I can do it the opposite way. I'm going to find the limit first, and then I'll square it afterwards. Just to be clear which limit laws I've used, if that, I'm going to come back to this, so if you're behind copying, that's okay. Just check this out. I'm going to go back to that limit law page. What have I used so far? I use this one to say, hey, I can put the limit on the top and the bottom if I want. I use this one to say I can do the limits of things adding and subtracting. I can do them separate first and add or subtract later. And then I use this one to say I can find the limit of something and do the exponent on it later. So I'm just grabbing out of these. The nice thing is you don't have to memorize this list. It's just like permission. That's what this page is permission to do all the things that you think, that you hope you'd be able to do with limits. Now I'm ready. I'll do the easiest of the 4 limits first. I think this one here is the easiest. Limit as x approaches 3 of x squared. Hopefully you did at least some of those in the homework. X squared is continuous. I'm not worried about a thing. I can just sub right into it. Limit as x approaches 3 of x squared is 3 squared. The next easiest one on the pile is this one. Limit as x approaches 3 of 7. But I'm going to hesitate for a minute because it's so easy it's hard. What does the function 7 look like? I almost gave it away. 7. Yeah, it's just 7 all the way across. It's a horizontal line at 7. So as you approach 3, there's not even really any subbing that you do here. The function says, my value is 7. And you go, well, what if you approach 3? And the function's like, asked and answered. I already told you. My value is 7. I don't care what you say. My value is 7. That's why I put that one as the second easiest limit on the piles, because it's just a little quirky, when you have a constant value like that. Now, top left, limit as x approaches 3 of f at x. I don't have f at x. How am I supposed to know what the limit as x approaches 3 of f at x is? It's given. That's the given. I'm finally down to using this given. See, I had to get those limits all the way through into the f at x, and the limit laws allow me to do that. And so when I get there, I don't know anything about f at x. F at x could be any function you want, except that we know that the limit as x approaches 3 of f at x is 5. And I can use this down here as well. Limit as x approaches 3 is 5, but I've got to square it afterwards. Then I do all the work. 5 plus 9 on the top, 25 minus 7, 14 over 18 equals 7 over 9. I did that all very fast, and I just want to refer to grade 9. 3 years ago, when you were in my class in grade 9, this was the type of question we sort of struggled with. Ooh, bed mass, all the steps. Now, I'm not mocking you. I'm just saying, when you struggle in math, in chemistry, in physics, in English, and you're like, oh, it's too hard, I can't do it. Just remember what was too hard at some point. That this was too hard at some point. Yeah? It'll all go better. So if you're feeling overwhelmed by anything, just remember how far you've come, and you can go that far again easily. Yeah? You're still young. How'd I do? Any questions about that crazy thing? Intimidating question because it looks like you haven't been given what you need, but it's actually pretty straightforward using the limit laws that we have. Oh, too fast? More time here? PowerPoint. Press the right button this time from current slide. Yes. Review the limit laws, my example. Some important functions. Oh, okay. So if you've drifted off to sleep or you have trouble getting your head going this morning, you're going to want to turn in for this. This is not particularly difficult, but it is very, very new. And so you're going to have to tune in to know what these next few slides are telling you. F at x equals sine x over x. You've seen sine x. You've seen x. You've seen rational functions. But sine f x over x has some very special properties that we need to talk about. There's sine x over x. If you put it in your calculator, you can graph it. Let's not get sidetracked by graphing it right now. But if you put sine x over x into your calculator, you'll get this thing. The only problem is it's got a hole at 0. I've given you none of the weapons it takes to really analyze that this would have a hole, except one, is that if we put 0 into both of these, we'll get sine 0, which is 0, over 0. So it's 0 over 0. The graph won't show it. Your graphing calculator doesn't show holes. Well, it does, but the resolution's too good. Let's just imagine we backed off the resolution of sine x over x. What you'd see if you really knock the resolution down was, it goes like this. That's what a hole really looks like in a graph. It's just a little tiny gap. The little circle we draw on it is like a magnifying glass. You know, it's like we tell everybody, look, there's a hole here too. Just let me show you. It's right there. It's that little circle. It's not really part of the graph. It's a circle you're using to go, look, there's a hole there. The problem is the resolution on the screen is so good, and it happens to be intersecting with the axis, you can't see it. You won't see a hole on the graph, on a calculator or something like that. But this thing has a hole. But the good news is this thing still does have a limit. The limit as x approaches 0 of sine x over x is 1. If you build a table of values in your calculator, you can definitely see it approaches 1 from both sides. You see, as you come in from the left side here, it goes to 99833. If you come in from the right side, it goes to 99833. It's heading towards 1. You can see it in the picture here. It's heading towards 1. It's a hole. But this limit is unbelievably useful. I saw some people doing what I was suggesting, which as soon as they got their test, they immediately write some stuff at the top of the test. They're like, I gotta remember this. This is number 1 for this chapter. Yeah? You really need to know that the limit of x approaches 0 of sine x over x is 1. If you've got your graphing calculator available, you can punch it in and remind yourself, but if it's in the part of the test that is you don't have your graphing calculator, you're just gonna need to memorize it. That one's got to get memorized. Here's another interesting function. It's called the greatest integer function. I'm going to get sidetracked. Sal, when you guys are programming and you're trying to decide if something's like divisible by 3, how do you guys, has that come up yet in your courses? Like you've got a number in, Emmett's maybe going to jump in here. How do you guys decide? Oh, so there's a remainder function. See, back when I was programming, we didn't have a remainder function. What we had to do was divide, find the integer value of it when you divided, find the not-integer value, and see if they were different. If they were different, you knew that was, okay, that's, okay, very good. I want to refer to it in my lesson, so I just wanted to understand how you use it. But you've got a function for it. Okay, f at x equals int x. It's called the greatest integer function. It rounds the value of x down to the nearest integer. So, what the int function does is it takes 3.7 and makes it 3. It doesn't round the way you were taught to round. See, you were taught to round to the closest thing. That makes sense. If someone says, here's $3.70, and you want to know the closest dollar is 4. Int's more like, what's the biggest thing you can buy? And if you've got $3.70, you don't have $4. You've got $3. That's what you can spend, and that's what int does. It rounds it down to the nearest integer. And it's notated by f at x equals square bracket x. This looks like it might be confused with other things, but it's actually doesn't come up as a big confusion problem. When we want to write int x, sort of like absolute value, remember absolute value had the straight lines? This now has these square brackets around it. Also known as the floor function. And let's take a look at what it would the graph would look like. Very strange looking. To really get to know the graph, let's talk about a few numbers. What would you round 1.1 down to? 1. So 1.1 rounds down to 1. How about 1.7? Rounds down to 1. Always rounds down. What about 2? Now you've got 2 full dollars. So it rounds down to 2. So you get these steps. This is often called the step function as well. Very convenient for rounding type situations, okay? Called the floor function because any number in that section just drops to the floor. Can you predict how the ceiling function works? Other applications you might want to round up all the time. And so anytime you get past, like if you get to 1.4, that immediately goes to 2. That one's not as useful, but this one is. You'll see some great homework questions on this. So 2 new functions, sine x over x. The big thing is knowing the limit there. And int x, knowing that, hey, you just round everything down. Oh, yeah. Yeah, yeah. Sorry, I'm just trying to decide if I've got room on here to do these or whether I want them on a separate page. And I'm going to go separate page on the off chance I get sidetracked on these. Oh, this one's left room underneath. Maybe I'm okay here. I'll give it a try. What kind of pen do I want today? Let's go with red. Okay. The only weapon I have to do these questions is this limit here. Limit as x approaches 0 of sine x over x equals 1. That's my weapon here. And just to really break down what that limit is telling you, it's telling you that, hey, if this variable is the same as this variable, and that variable is heading to 0, I'm home free. The answer is 1. But these have a little more to it than that. This is 5x. It's the same as 5x down there, but it's not 5x over here. You might be able to look at that one and go, well, I can see what's going to happen anyways. And that's fine. But when they get a little tricky, you're going to want another weapon that I showed you yesterday, which is called change of variable. I'm going to go, oh yeah, to really make this look like that, I'm going to go let u equal 5x. It's such a smooth move. It's such a little tiny move, but it's so smooth in that this now is going to be what I want. Sine of something over something, that's all going to work out. The other thing to notice is that as x goes to 0, what's going to happen to my u value? And you can just sub it in. You sub in x equals 0 there. U will go to 5 times 0. U also goes to 0. So now I'm ready to rewrite this limit with u's instead of x's. This thing equals limit as u approaches 0 of sine u over u. If you're unimpressed and you're like, well, I knew what was going to happen anyways, I know, but I've given you a powerful weapon here. When the variable isn't what you want it to be, change it and roll with it. You know what I mean? Just keep right on rolling. Now look at this. Limit as u approaches 0 of sine u over u. Now it does look the exact same. Same variable top and bottom, and the variable's heading towards 0. Answer here is 1. You're like, oh, they're all going to come out to 1 then. No. That one was just set up that it worked out nice like that. Next one. Limit as x approaches 0 of sine 9x over x. There's different ways to handle this situation. Do you see now that what's in the side the sine is not what's in the denominator? It's 9x and x. It's different now. So here's my move. Here's what I like to do. And I don't even write it on a new line. As I go, okay, I'm going to multiply by my favorite number. Here it is again. It comes up so often. My favorite number is 1. I'm going to multiply by 1. I'm going to multiply this top by 1. And I'm going to multiply this bottom by 1. And do you see now that what's in the sign is the same as what's in the denominator, which I love. So, this is all beautiful, but I got this extra 9 here. We learned in limit laws, multiplying by 9, I can do it before or after the limit. So I'm going to just bring it up front. Oh no, this is what I hate about PowerPoint. Just a second. Find our options. Eraser. Okay, is it a... Oh, it's much better. The old one, as soon as I hit erase, everything would erase. They've upgraded. Thank you, Microsoft. Back to my pen. Sine 9x over 9x. I think that's really easy. But if it's not, you need to tell me right now, because that is what changes these questions from sort of easy to difficult if you don't understand what I did there. I multiplied by 9 over 9. 1 9 I left in there, so these would match up. The other 9 I pulled it out front, so it wasn't in the limit anymore. And that's limit laws. Limit laws are, you want to multiply by 9 now? Go ahead. You want to multiply by 9 later? Go ahead. Limit laws are friendly like that. Good? Who wants the next step? Now what should I do if I really want to formally do this? You may be already able to see exactly what's going to happen here. But if I want to make it really look like this, what would my next step be? Yeah, I like this let u equal 9x step. And then a little note to say, well, as x goes to 0, u goes to 0. I just sub that in and go, okay, I'm still going to have the same limits as I did before. Yeah? That can change sometimes. Don't assume these are going to be the same. It can change. It just hasn't changed yet. So what I get here is, and I see a question coming, so let me just write this all in here. Limit as u approaches 0, sine u over u, and I'm ready to finish this question off. I only need 2 more lines. Question? What I'm saying is that whatever I get in this limit here, I'm going to have to multiply it by 9 afterwards. It was a multiplier inside before, multiply by 9. I said, okay, yeah, I'm going to multiply by 9. Don't panic limits. I'll put it up front, and I'll multiply by 9 at the end. And limit laws totally allow you to do that. Multiply by 9 first, great. Multiply by 9 after, no problem. Limits are friendly like that. What's the value of this limit here, sine u over u? 1. You see how important it is. It's not complicated. But if you don't have that memorized, oh boy, you're in trouble. You can't do these questions. You don't know what you're trying to accomplish in these questions. So it quickly becomes the most important memorizing in the chapter. So 9 times 1 is 9. There's ways to shorten these things down. I'm showing all the steps to really explain it. Oh, here we go. Limit as x approaches 0 of tan x over x. This is how we ain't got no tans. If only there was a way to use tan and get back to sine. Never go far without your trig toolbox. Oh, Will wants to answer anyways. Will, what do you like here? If there's going to be a way, and I don't say every trig identity, every trig limit out there is solved by substitution with other trig identities. I'm not saying that's true, but if there's going to be a way, we've got to get sine x involved here. So tan x is sine x over cos x, and that's all over x. Now, the real problem with trig identities in grade 11 and 12 often was not the trig identities, it was your fractions. Is that your fractions you have holes in your fraction abilities. One thing I would suggest is when you get a fraction inside a fraction like this, if it's confusing to you, write them separately. It got so bad one year around here, I said never write a fraction inside a fraction. Always write it like this. And that might tip you off about what has to happen next. Dividing fractions, we multiply by the reciprocal. So this becomes 1 over x. And I get this. Numerator times numerator. Denominator times denominator. I might show this video to my grade 9s who just want to use their calculator to do fractions. Now that they've seen it can do it, I'm like, yeah, if life was about 3/4 plus 1/2, yes, we'd all use calculators to do fractions. But we're up to something. We have to be able to handle crazier fractions than that. Now, can you see it? What has to happen here? It's almost there. It's kind of there, but it's not. Give this a stare down for a second. Sine x over x. Give this one a stare down. Sine x over x. Think about limit laws for a second. I'm letting your brain work now. So come test time and homework time, you at least have pounded your head on this a little bit. Do you see sine x over x in there? It's in there. Yeah. Pull them apart. Limit laws are so friendly. So I can pull this out, and he wants to pull it out front. It could be out back as well. I got this, the cos x out front, but in the denominator. It was in the denominator. And then I've got this part here. Now, we really got to talk about this for a second because there's a lot going on here. What is the basic, very basic strategy for evaluating limits? What's your first attempt always? Factor comes a little later. Factor comes if things go badly. Sub's the move. Okay? Now, the reason sub doesn't work on sine x over x is when you put 0 in there, you get 0 over 0. So now I've given you a new weapon today, which is, I can't deal with all the 0 over 0s, but you've got these choices when it's 0 over 0. You've got factoring. You've got rationalizing. You've got u substitution. You've got absolute value. And if it happens to be sine x over x, you know the answer is 1. So this part I can do. Not by substituting, by knowing that this is a 1. Back to here. What's our first move when we're trying to do limits? Substitution. And you assume that substitution won't work because substitution wouldn't have worked had I used it up here. Well, substitution will work on the cos part. Cos doesn't have a problem here. Cos of 0 is 1. And so I got 1 over 1 times 1 is 1. Question? Why did I just bring the 9 up front? Or why didn't I put the limit on it? Is that what you mean? Yeah, I really should have wrote limit as x approaches 0 of 9 in front of that, except that it was a constant. So I knew it was going to be 9. It's always 9, so the limit's, So, but technically speaking, you're right. This should have had a little limit as x approaches 0 in front of it when I pulled that out like that. Yeah, that was a little sloppy. A little sloppy teaching, not necessarily sloppy doing when you're doing it yourselves. That really is just like a common factor that goes out front of the whole thing. Other questions? Okay, int. You just got to draw the graph for int. Finding limits of int is pretty straightforward if you just stare at the graph. Limit as x approaches 3. Where's my graph of int? There it is. As x approaches 3. Okay, I got to add the next part of int on my graph here. I've got my graph of int. What's the limit as x approaches 3 of int? Yeah, can't do it. Can't do it. Any of the whole numbers aren't going to work here. And again, for int, I really suggest drawing the graph as soon as an int limit comes up. Get a graph and you can see what's going on. How about 4.5 though? Look back to the graph. There's 3. There's 4. There's 4.5 right there. What's it heading towards? Weirdly. 4. Yeah, so when you're in the middle there, it's going to head towards 4. 4.6 is heading towards 4. 4.4. They all agree in that part of it. So an int, when you're in the integer part, and again, C graph. And even if they go to really big numbers, say they go to 104.5, you can do 4.5, you can do 104.5. The graph will definitely help you there. Questions on int? How are we doing? How much more time do I got? Sandwich? Just fast forward. Oh, just sandwich theorem. Okay, keep all that stuff, and we want sandwich theorem. More time on previous slide, he says. This one? Well, that's all my writing. You want all this? Oop. There. Last slide of this part of the lesson. Then maybe we'll take a little breather, and then I'll go again, because I want to be done by 11. I think, Brad, you're one of the ones, yes? That's why. Can I do that other lesson by 11? Ooh, it's going to be tight. Okay. Sandwich theorem. Oh, very technical language here. Let me draw a picture of sandwich theorem first. Okay? Then we'll come back to the technical thing here. And it might be the same picture that's going to come up in your PowerPoint in just a second. Say I've got a graph that heads towards 0. And I've got another graph that heads towards 0. And I know there's a third graph that's trapped between those two. Yeah? It's like in here somewhere. And it's trapped between those two. If I know this one heads to 0, and this one heads to 0, and this one's trapped between, it's got to head towards 0 too. It doesn't have any choice. That's as simple as sandwich theorem is. And there's a great way to set it up and use it. Beautiful theorem, pretty simple stuff, and sort of fits with what you think would happen. So, if g at x is less than f at x is less than h at x, that is f at x, you see it's trapped between g and h. And g and h both head to some limit, then f will head towards the same limit. It's trapped between them. It's got to head towards the same spot. If the values of the function f are always between g and h have the same limit, then f has that limit too. Here's a nice picture of it. See, g and h are both heading towards this limit L. I made that picture on the board there 0, but this picture is much better because it says it doesn't matter what the limit is. H is heading towards this limit. G is heading towards this limit. If the blue line is trapped between, it's got to head towards the limit too. We don't do a rigorous proof here because it's like too obvious. It's got to be. It's got to go there if it's trapped between these two. Just one example? Oh, here's the graph, by the way, but I'll do the algebraic version of this. Okay? New page. Take picture. Hey, don't be like that, silly rabbit. Here's the example. We got a nice graph there, but that doesn't help us to do this question algebraically. Take a look at this. Sandwich theorem at a basic level usually involves sine or cosine because sine and cosine have nice rules about them. I'm going to write a statement that I hope you look at and go, yes, I totally get that. I totally agree with that. -1 is less than or equal to sine x is less than or equal to 1. Are we 100% in agreement with that? Sine x is trapped between -1 and 1. And what that means is I can go a step farther and to say -1 is less than or equal to sine of 1 over x is less than or equal to 1. The fact that it's 1 over x in the brackets doesn't change that. Sine can only spit out numbers between -1 and 1. It doesn't matter how the input got there. No matter what you do before that, sine eventually goes, here's an answer between -1 and 1. Can you see what I'm up to here? I'm building what's going on here. I'm building this thing with these restrictions, these sandwich restrictions on it. Sine of 1 over x is trapped between -1 and 1. Now I'm going to multiply everything by x squared. That's phase 1 of sandwich theorem. What phase 1 has accomplished is I've taken my function that they wanted to find the limit of, and I've trapped it between two things. I've got this thing trapped now. Now, for sandwich theorem to work, the limits of the outsides have to be the same. So, limit as x approaches 0 of the negative x squared. What's the limit of this part over here? If x is heading to 0, what happens to negative x squared? 0. How about the right-hand side of this thing? Limit as x approaches 0 of x squared. What's that one heading towards? 0. Take a look at the picture. The two pink lines are x squared and negative x squared. Can you see them there? As you approach 0, they both head towards 0. X squared and negative x squared aren't very similar functions, really. But as you approach 0, they both head towards 0. And so now I've got, therefore, limit as x approaches 0 of x squared sine 1 over x. What's it got to head towards if it's trapped between these two things? It's also got to head towards 0. Then someone raises their hand and says, couldn't I have just subbed in right at the start? Why doesn't subbing work? Big moment. I'm sorry if your brain has gone fuzzy here. I'm just getting a flashback from this test I just wrote for you. Why doesn't subbing work on this particular question? I can sub the 0 in here. There's the 0 I want. There's the answer, isn't it? Sine of 1 over... Oh, subbing doesn't work. Even though you want it to work, and even though it works out to be the right answer, it didn't have to work out to the right answer. It just happened to be nice here, be nice and friendly, okay? So just a final note in red pen to draw your attention to it. Subbing won't work. 1 over 0 is undefined. Questions about sandwich theorem? Well, I'd love to keep going. How are we doing? Are we okay? We're okay. I'm doing a favor to those people who have to leave for 40 minutes so they get to see the lesson live. And things like this are annoying when you have a teacher like me who's trying to do their best for everybody. It's like getting tests back from me is sometimes difficult. I mark them, you can get your mark back, but you can't look at them because I'm being kind to the people who are away and making sure they're ready. And if it ever happens to you, you're going to be glad I'm kind. And I'm being kind here by teaching a bunch more. Who are the people that have to go? Here, I've got the email right here. I'm going to stop that video.